Hello, AP Chemistry students. We're now at Unit 5, Part 2, which is going to wrap up Unit 5 with a focus on reaction mechanisms, which will cover sections 5.4, 5.7, and then 5.9 through 11. Our learning objectives are to represent an elementary reaction as a rate law expression using stoichiometry, to identify the components of reaction mechanisms, to identify the rate law for a reaction from a mechanism in which the first step is not rate limiting, to represent the activation energy and overall energy change in a multi-step reaction with a reaction energy profile, and to explain the relationship between the effect of a catalyst on the reaction and the changes in the reaction mechanisms. So in this lecture, we're going to talk about how reactions happen, what their mechanisms look like. And reactions can be very complex and are usually broken into multiple steps called elementary reactions. And this describes a process where one or more chemical species react directly to form products in a single step with a single transition state or activated complex. And this is all according to collision theory, which we talked about before, where two atoms or molecules need to collide in the right orientation with the right amount of energy to create a transition state or activated complex, which is a big heap of atoms that are unstable, that then relaxes into a new set of stable products. So let's talk about the types of elementary reactions that can occur. Sometimes there's no collision at all. And a reaction where no collision occurs and a single reactant decomposes or changes into something else is considered to be a unimolecular. So example here we have PCl5, which is decomposing into PCl3 and chlorine gas. A reaction where two reactants collide to form a product, the normal type of thing we think about with collision theory, is called a bimolecular elementary reaction. And that can be either a reaction between two of the same type of chemical colliding or two different types of chemicals colliding. And sometimes a chemical equation indicates that three substances are colliding, in which we would have a termolecular or trimolecular elementary reaction, like in this case where we have two ICl2s reacting with one hydrogen gas. However, if we think about collision theory and we think about how two particles need to collide with the right energy and orientation for a reaction to occur in the first place, if we think about the likelihood of three particles all colliding with the right amount of energy and the right orientation, we realize that this is very, very, very unlikely to occur. So most equations that represent termolecular or trimolecular equations aren't elementary reactions at all. And actually what happens is that this reaction occurs stepwise in a series of bimolecular elementary reactions. And it's considered to be a non-elementary equation overall. For example, this equation we talked about above can actually occur in two steps, where one ICl2 reacts with a hydrogen gas instead of two, and we form ICl and HI, and then this HI collides with another ICl2 to make another HCl and I2. And you'll see that if I sum up these two equations together, I'll end up with this equation overall. And this HI that was formed in the first step is going to be immediately consumed in the second step and not be a part of the overall chemical equation. So a stepwise reaction is going to have multiple activated complexes, one for each of the individual steps. And each of these is going to have their own likelihood of formation, their own likelihood of those particles colliding with the right energy and orientation, and they're all going to have their own activation energies. So therefore, each individual step in a multi-step reaction is going to have its own kinetics. And we can see here in this reaction energy profile, as the reaction progress proceeds, we end up with two separate bumps. This first one representing the first step of the reaction, this being the energy that it needs to collide with in order to make the first activated complex. That's going to collide, or that's going to decompose into some products, and then those products are going to collide with something else. We're going to have another activated complex, and then that's going to relax to form the products overall. But we can see here that based off of this graph, each step has its own activation energy, and at each of the tops of the humps here, there's going to be a different activated complex. If we want to determine the rate law for an elementary reaction, we can usually infer it from the stoichiometry of the particles colliding. The assumption that we make here is that the rate order for each of the chemical species in the elementary reaction is going to be based off of its stoichiometric coefficient. For example, If we have a unimolecular reaction where 1 mole of A is decomposing into products, it's going to be first order in A, and our rate law is going to be rate is equal to K times the concentration of A, because the rate in which the product is formed is going to be based off of the initial concentration of A to begin with. For a bimolecular reaction, it's going to depend on whether we are reacting two dissimilar chemicals or two similar chemicals. Because if it's two dissimilar chemicals, it's going to be first order in each of those individual reactants. So for A colliding with B, we're going to have a rate law of rate is equal to K times the concentration of A times the concentration of B. But for a reaction where two of the same substance are colliding, this is technically 2 moles of A making a product. Therefore, it'll be second order in A. So our rate law will be rate is equal to K times A to the second power. For termolecular reactions or the more complicated multi-step reactions, it's going to be based off of the individual components involved. So A, B, and C, it's going to be first order in each of those substances. If there's 3 moles of A all colliding, it's going to be A to the third power. It's going to be third order in A. And if we have 2 A's colliding with 1 B, that's going to be second order in A and first order in B. But as I mentioned earlier, termolecular reactions are very unlikely to occur with these sorts of mechanisms. So let's talk a little bit more about how multi-step reactions can be applied to this logic. So imagine this overall reaction. It happens in 2 steps. So 2 nitrogen dioxides are going to collide to make 1 nitrogen trioxide and 1 nitrogen monoxide. And in the second step, the nitrogen trioxide that we formed is going to collide with a carbon monoxide to make carbon dioxide and nitrogen dioxide. If we want to look at the overall reaction, we can add both of these steps together, adding up all of the stuff on the reactant side and adding up all the stuff on the product side, and then canceling out things that appear on both sides, aka this nitrogen trioxide molecule that gets made in the first step and then consumed in the second step. Then we get the overall reaction of carbon monoxide plus nitrogen dioxide, making carbon dioxide and nitrogen monoxide. As I mentioned earlier, the NO3, since it's on both sides, we consider this to be an intermediate. So this is a substance that is being formed in the chemical reaction that is not part of the overall reaction because it is made and then it is consumed. If we want to determine the rate law of a multi-step reaction, we need to figure out which step in the reaction is going to have the biggest impact on the rate. Because like I said before, each of the steps is going to have its own kinetics involved with it. It's going to have its own activated complex and its own activation energy and its own likelihood of occurring. So let's look at this reaction again. So for step 1, this is measured to be the slow step, and then step 2 is measured to be a fast step. What that means is that step 1 is going to have a more impact on the overall rate of the reaction than the second step. And it's therefore going to be the main factor that we consider for the rate law. And this slow step we call the rate limiting step or the rate determining step. And we're going to make a rate law that is based off of the concentration of the reactants in this slow step raised to the power of their coefficients. So for example, since step 1 is our slow step, our rate determining step, we could see that the reactants are NO2, and there's 2 of them, so it's second order in NO2. So therefore, our rate is equal to K times NO2 to the second power. Even though in the overall reaction we have carbon monoxide as one of our reactants, it's not included in the rate law because it is not part of the rate determining step. In the last example, the rate determining step was conveniently the first one, which meant it didn't have any intermediates or anything like that could complicate it. But let's look at an example where the second step is the rate determining step instead of the first. And in this reaction, we have overall 2 nitrogen monoxide reacting with bromine to make 2 NOBr. In the first step, which is our fast step, we have NO reacting with Br2 to make NOBr2, which is an intermediate, which is then used up in the second step by colliding with NO to make 2 NOBr. And this second step, being the slow step, is going to be dependent usually on the 2 reactants that make it up. However, NOBr2 isn't really a reactant. It's not even in the overall reaction because it's an intermediate formed in the first step. And rate laws are usually based off of the initial concentrations of substances. An intermediate doesn't have an initial concentration. So therefore, it doesn't have a concentration that we can put into the rate law. So this complicates things. And in this, we apply something called the steady state approximation. And to do this, we assume that intermediates that are formed are consumed instantaneously and therefore have a constant and negligible concentration. And we can estimate what the rate law is going to be, assuming that the production of that intermediate is going to be based off of the orders of the components that are colliding to produce it. What I mean by that is the existence of NOBr2 in the reaction is based off of this first reaction. So even though the NO and Br2 are colliding to make NOBr2 in a fast step that's not rate limiting, the initial concentration or the concentration overall of NOBr2 in the solution is going to be dependent on that reaction happening. So therefore, we can take this intermediate, and when we're making the rate law, we can substitute it out for the products or for the reactants that collided to make it. So for example, we would have normally written the rate law as rate equals K times NO times NOBr2, both to the first order, because that would be based off of the stoichiometry of the rate determining step. However, since NOBr2 is an intermediate and we can't include it in the rate law, we're now going to substitute NOBr2 for the things that made it in the first step and their stoichiometric coefficients as rate orders. So therefore, the NOBr2 becomes NO and Br2, and then therefore our overall rate law becomes rate is equal to K times NO to the second power and Br2 to the first power. Let's look at another example. Given the following elementary steps, determine the overall reaction and the rate law given this stepwise process. So in our first step, we have NO2 reacting with F2, which makes NO2F plus F. And then in the second step, and this is our slow step, our rate determining step. And then in the second step, the NO2, another NO2, is going to react with the F that we made in the first step to make another NO2F. So to get the overall reaction, we're going to want to sum everything up and then cancel out everything that appears on both sides. We can see that the F being produced in the first step is consumed in the second step, so those are going to cancel out. So we're going to have NO2 times 2, since there's one in the first step reacting and then one in the second step reacting, plus F2 to produce 2 NO2Fs. And then to get our rate law, we are going to look at the rate determining step, and we could see that it is a bimolecular elementary reaction involving the collision of one NO2 and one F2. So that means that our rate is going to be first order in NO2 and first order in F2. And even though it's two NO2s in the overall reaction, only one of them is being used in the rate determining step. Let's try another example with a three-step process. So in step 1, we have A plus A making X, and this is a fast reaction. In step 2, we have the X from the first reaction colliding with a B to make C and Y, and this is our rate determining step. And then the Y that we got in the second step is then going to collide with a B to make a D, and this is another fast step. And from this, we want to determine the overall reaction and the rate law. So we can start summing everything up. If we were to do this, we'd end up with 2A plus 2B making C and D, because we can identify that the X and the Y are going to be intermediates. The X is produced in the first step and consumed in the second, and then Y is produced in the second step and then consumed in the third. We had 2A's reacting in step 1, and then 1B from step 2, and then 1B from step 3. And then overall, the products that we make are 1C and 1D. Now, if we want to determine the rate law, it's going to be based off of the rate determining step, which is step 2. And since step 2 has an intermediate X in it, we're going to substitute out X for the things that made it, which were 2A's. Therefore, our rate is going to be equal to K times A to the second power times B. It's second order in A due to the 2A's that collided in the first step to make the X intermediate, and then that X intermediate reacts with the 1B, so then is therefore first order in B. Another important component in chemical reactions, and an important component when considering reaction rates, is a catalyst. And a catalyst is defined as a substance that lowers the activation energy of a reaction. It does so by altering the reaction mechanism and providing a lower energy means of progress through a more convenient and lower energy activated complex or transition state. And a catalyst is never consumed in a reaction. What all that means is that a catalyst is something that kind of helps a reaction along by making easier to form transition states. And the catalyst is never going to be consumed. It's never actually going to be a part of the overall reaction. And its concentration is going to be the same as it started with. And if we were to look at the effect of a catalyst on a reaction energy diagram, we could see that this purple line represents the uncatalyzed reaction, where we have an activation energy corresponding with this distance. And then when we add a catalyst to it, we can see that the overall energy of the reactants and the products are exactly the same. The overall energy difference between the reactants and products, how much energy is being consumed or released in the overall reaction, is going to be the same. But we can see that the hump has gotten smaller. The energy of the activated complex is lower than that of the uncatalyzed reaction, and that helps it proceed much faster. And if we were to look at that in terms of chemical mechanisms, let's look at the following reaction of A plus B making C. And we want to add a catalyst X to the reaction, which is going to turn this bimolecular elementary reaction into a multi-step process, where in step 1, the A collides with X to make AX, which is an intermediate, and then this intermediate is going to collide with B to make C and X again. And this is sort of the key part to a catalyst, where the catalyst is there in the first step, and then it is there again in the last step unchanged. It has not been consumed by the reaction. And let's look at a real life example of this. So you might know the elephant's toothpaste reaction, the one where you decompose hydrogen peroxide using a catalyst and it produces all that foam if you add soap to it. Well, the reaction that's actually happening there is two hydrogen peroxides decomposing into two water molecules and an oxygen molecule, and that oxygen is what makes the soap foam up. And this is a process that can be catalyzed by Ki. Potassium iodide or sodium iodide also works. And this is what happens in the elephant toothpaste experiment because it is happening all of a sudden. You might know that hydrogen peroxide comes in brown bottles because it is likely to react and decompose into water and oxygen if it's exposed to light. And this happens very, very slowly. But in that elephant's toothpaste reaction, it happens extremely quickly because a catalyst is being added, which then helps the reaction proceed faster. And what that looks like is in the first step, the iodide reacts with one hydrogen peroxide to make one water molecule and an OI minus, which is an intermediate, which then runs into another hydrogen peroxide to produce yet another water molecule and an oxygen. And we can see here that we get iodide at the end, and which further proves that iodide is a catalyst because we started with it. It got used in the reaction and it made an intermediate, but we spat it back out at the end unchanged. So overall, the I minus concentration is going to be the same at the end as it was at the start. Now, if we determine the rate law for this catalyzed reaction, we're of course going to base it off of the rate determining step. So what it's going to look like is this, where the rate is equal to K times the hydrogen peroxide concentration times the iodide concentration. Now, unlike intermediates, catalysts can be included in the rate law because they do have initial concentrations that will affect the rate law. You'd probably notice that depending on the amount of iodide that you added to the reaction, it's going to alter the rate in which the reaction occurs. And I've actually made a video demonstration of this reaction to kind of further show this point. So usually with the elephant's toothpaste reaction, we add soap and food coloring, and this is what it looks like. Come on, play. So we have the hydrogen peroxide with food coloring and soap in it. I added some potassium iodine. You can see it starts to foam up from the rapid production of oxygen gas. And that creates this big foaming effect that you might be used to seeing from internet videos. I did it on kind of a small scale, but It's still kind of fun to watch. Now, I did a follow-up experiment with this, where instead of doing it the old-fashioned way with the food coloring and the soap, all I did was add just straight potassium iodide to hydrogen peroxide, because I think there's a kind of a cool thing that you can see during this process. Let's have a look. This one took a little bit longer, so it's sped up. So you can see that it turns like a yellowish color. That's because of the IO minus intermediate. And you can see that it's starting to react. It's fizzing. It's producing a bunch of oxygen gas. And you can see over time that that yellow starts to fade. And at the end, we end up with a clear solution. And that is sort of indication that we had an intermediate form that had a different oxidation state of iodine and therefore a different color. And then that intermediate was consumed at the end because that yellow color was produced and then it went away at the end. All right, and that is all for Unit 5, Part 2, and I'll see you in Unit 6.